Imagine a bridge so vast, it could finally connect two lands separated for more than 1,000 years. This is not a concept on paper. It is not a dream in an engineer's notebook. It is the world's longest suspension bridge, and against every doubt, it is really happening. 3.3 kilometers of open water stand in the way. No island to break the distance, no midpoint to rest on. Just one continuous span, unlike anything ever attempted in engineering history. For decades, experts insisted it could not be done. The seismic risk was too great, the winds too violent, the distance too vast. Now Italy is proving them wrong, one carefully engineered stage at a time. This is the real story of how they are building the Strait of Messina Bridge, from the first survey ship to the final beam of light across the water. On one side lies Sicily, an island separated from mainland Europe since the earliest chapters of recorded history. Its people long dependent on the sea for every crossing. On the other lies Calabria, the toe of the Italian boot, its coastline staring back across the strait for generations. For centuries, the only way across was by boat, slow, costly, and at the mercy of storms. Now, a single continuous structure will replace it all, 6 lanes of highway and 2 dedicated railway tracks, carrying both people and freight in one unified crossing. This is a project 3,666 meters in length, engineered from the outset to endure for more than 2 centuries. Its main span alone will stretch 3.3 kilometers, nearly double the length of any suspension bridge ever built on Earth. 2 towers will rise nearly 400 meters into the sky, taller than almost every skyscraper on the continent, anchoring the structure at either end. Every meter of this coastline is being reshaped to withstand forces no ordinary bridge has ever had to endure. But before a single piece of steel can rise, the land itself must be understood, tested, mapped, and prepared. This is where the true story of construction begins, not with towers, but with knowledge. Long before construction starts, survey vessels move methodically across the strait, mapping every contour of the seabed. Sonar and seismic sensors reveal what lies beneath, layers of rock, shifting sediment, and the fault lines that define this region. The Strait of Messina sits within one of the most seismically active zones anywhere in the Mediterranean basin. As a result, engineers must design for far more than weight and wind. They must account for earthquakes exceeding magnitude 7. Deep core drilling rigs bore hundreds of meters into the seabed, extracting rock samples that will guide every structural decision. Each sample tells engineers precisely how the ground will behave under extreme, sustained load. Dozens of boreholes are drilled across both the Sicilian and Calabrian coastlines, building a complete geological picture. On the mainland, geologists study centuries of fault movement, tracing seismic patterns back thousands of years. Wind data is gathered too. This narrow strait channels some of the most powerful and unpredictable gusts in southern Italy. Fast-moving tidal currents beneath the surface add another layer of complexity to every structural calculation. On the Sicilian shore, large-scale excavation begins, carving out space for the tower's foundation. Millions of cubic meters of rock and soil must be removed before a single tower can rise. Deep foundation shafts are drilled directly into solid bedrock, anchoring the tower's immense weight. Each foundation must support a structure nearly 400 meters tall, standing firm against relentless coastal wind. Specially engineered concrete, reinforced with seismic-resistant steel, begins to pour, layer upon layer. Every pour is monitored for strength, density, and curing time, following some of the strictest standards in the world. Across the strait, an identical foundation begins to take shape on the mainland, mirroring the work in Sicily. These foundations must reach deep enough to resist both violent earthquakes and hurricane-force winds. steel reinforcement cages, some weighing hundreds of tons apiece, are lowered into position. Once cured, this concrete base will carry a load greater than any bridge foundation ever built. Nearby, similar preparation begins for the massive anchorages that will hold the entire suspension cable system. These anchorages must resist forces powerful enough to hold the full weight of the deck and everything crossing it. Engineers embed massive steel and concrete blocks directly into the mountainside, fusing structure with landscape. Each anchorage will eventually resist a pulling force greater than the weight of an aircraft carrier. 2 coastlines, 2 matching foundations, 1 shared objective, connecting a land divided by water. The anchorages begin to rise from the ground, colossal concrete structures built to grip and secure the suspension cables. Layer by layer, thousands of tons of reinforced concrete are poured into place with meticulous precision. Each anchorage is engineered to remain stable, even as the cables pull with tens of thousands of tons of tension. On the mainland side, its twin anchorage takes shape with the same scale and precision. Inside each anchorage, massive steel plates are cast directly into the concrete core, linking cable to earth. These structures are so immense that, once complete, they will resemble small, man-made mountains. Heavy cranes begin positioning the final structural elements of the anchorage housing. Curing takes several weeks, with constant monitoring to ensure the concrete reaches full strength. By the time construction concludes, these 2 anchorages alone will rank among the largest ever built. With the anchors firmly set, attention turns skyward, toward the towers that will define this skyline. At nearly 400 meters in height, these twin towers will become the tallest structures anywhere in Italy. Construction begins from the base upward, a reinforced concrete core engineered to flex under pressure rather than break. Climbing formwork systems allow each tower to rise in continuous, precisely measured vertical sections. Every section is poured, cured, and rigorously tested before construction moves to the next stage. As each tower climbs, engineers continuously monitor vertical alignment, measuring deviations down to the millimeter. Wind sensors are installed early, since these towers must withstand gusts exceeding 200 kilometers per hour. The tower's distinctive twin-leg design distributes structural stress evenly, letting it sway safely under extreme load. Day after day, the tower climbs steadily higher, a slow, disciplined race toward the clouds. Concrete is pumped hundreds of meters upward through a continuous vertical supply chain. At this extraordinary height, the tower begins to disappear into low-hanging clouds on humid coastal mornings. Across the strait, its twin rises in near-perfect synchronization on the Calabrian side. For the first time, the true scale of this crossing becomes visible. 2 towering giants facing one another across open water. Near the summit, the 2 tower legs gradually taper inward, merging into a single unified structural crown. From nearly 400 meters above the sea, the strait below appears as little more than a narrow ribbon of deep blue. The tower is finally complete, the tallest man-made structure this ancient coastline has ever witnessed. At the very top, enormous steel saddles are installed to guide and support the suspension cables that follow. Before the main cables can be spun into place, a temporary catwalk must first be constructed across the entire span. This narrow, suspended walkway becomes the foundation for one of the most delicate stages of the entire project. A process known as aerial spinning now begins, pulling thousands of individual wires across the full width of the strait. Each wire, no thicker than a human finger, will eventually become part of a cable, stronger than steel itself. More than 20,000 individual wires will ultimately be spun together to form each of the 2 main suspension cables. Slowly, strand by strand, the cable grows from a single thread into a solid structure more than a meter in diameter. For the first time in this project's history, Sicily and Calabria become physically linked, connected by one continuous cable. The cable's graceful, sweeping curve is not simply aesthetic. It is precise physics, distributing tension evenly across the entire span. Hydraulic compactors squeeze the finished wire bundle into a dense, weatherproof cable core, ready to bear enormous structural loads. A tightly wound protective wrap seals each cable against corrosion, engineered to endure for the next 2 centuries without failure. 2 massive main cables now stretch, unbroken, from the shores of Sicily to the Italian mainland for the very first time. Each individual cable alone is capable of carrying a load equivalent to thousands of fully loaded heavy trucks. At each end, the cables lock securely into the massive anchorages constructed months earlier, completing the structural circuit. The skeletal framework of the bridge is now complete. It is finally time to build the surface that people will actually cross. Away from the strait itself, massive prefabricated steel deck sections are fabricated piece by piece at a dedicated coastal assembly yard. Each deck segment is aerodynamically shaped, thin and light enough to slice cleanly through even the fiercest coastal crosswinds. Once finished, these segments are loaded onto transport barges, ready to begin their journey to the strait. One by one, deck sections are floated directly beneath their final designated position, suspended high above in the open sky. Powerful lifting systems, anchored directly to the main cables above, begin raising each segment into place. Inch by inch, an entire piece of finished roadway rises nearly 70 meters above the sea. Once precisely aligned, each segment locks into position, connected directly to the suspension cables overhead. The process repeats continuously, segment after segment, slowly stitching a complete deck together across the open strait. Construction advances simultaneously from both towers at once, engineered to meet with absolute precision at the exact center. Every structural joint is engineered to flex slightly under pressure, absorbing both wind load and seismic movement. Slowly but steadily, a continuous roadway takes shape where, until now, there had only ever been open sky. The final remaining gap, the literal midpoint between Sicily and Calabria, grows visibly smaller with every passing week. And then, at last, the defining moment arrives. The final deck segment is carefully lowered into its designated place. For the first time in recorded history, Sicily and the Italian mainland become physically joined by continuous, solid structure. 3,666 meters of unbroken structure now spans the water below, from coastline to coastline. With the deck now complete, work shifts toward the systems that will actually move people and goods across it. 2 dedicated railway tracks are installed along the central spine of the deck, engineered for both freight and passenger service. On either side of the tracks, 6 full highway lanes take shape, 3 lanes of continuous traffic running in each direction. Massive expansion joints are fitted throughout the structure, allowing the bridge to flex safely with temperature and wind. Lighting, drainage, and structural monitoring systems are woven into every meter of the finished bridge. Thousands of embedded sensors now monitor stress, vibration, and structural movement across the bridge in real time. On the mainland, more than 40 kilometers of connecting roads and tunnels link the bridge into Italy's wider transport network. Underground rail links ensure trains can move seamlessly from the bridge into the national railway grid. On the Sicilian side, new interchanges are engineered to safely absorb the coming surge in daily crossing traffic. Specialized seismic dampers are installed at every critical point, engineered to absorb the shock of a major earthquake. Before a single vehicle is permitted to cross, the entire structure must prove itself under extreme, rigorous testing. Engineers simulate the combined weight of thousands of vehicles and trains crossing the bridge simultaneously. Every measurable vibration, every millimeter of movement, is checked against decades of detailed engineering models. Wind tunnel and live testing confirm exactly what engineers designed this bridge to achieve: controlled movement, never catastrophic failure. For the very first time, the bridge is illuminated after dark. its lights visible simultaneously from both coastlines across the strait. It is no longer simply a construction site. Piece by piece, it has become a genuine landmark of modern engineering. Final inspections move methodically, end to end, checking every weld, joint, and cable connection one last time. The finished roadway now sits in complete silence, fully ready, yet not quite open to the world just yet. Every stage of this project, from the earliest seabed survey to the final structural weld, has led to this one unbroken structure. 3,666 meters, 2 soaring towers, one truly impossible span, finally made real. What was once 1,000 years of physical separation has, at last, become a single, unbroken crossing between two lands. This is more than steel and concrete. It is the story of human ambition, engineering precision, and the refusal to accept impossible limits. The Strait of Messina Bridge now stands as living proof that even the most impossible crossings can, in fact, be built. If this story moved you, that genuinely means more to us than you know, because every view helps us keep telling stories exactly like this one. Subscribe to our channel. It costs you absolutely nothing, but it means everything to us. Thank you for watching the real story of the world's longest suspension bridge.